Hi guys, welcome back to my channel, and this is the day for our DSA bootcamp. I will be starting with the GFG portal, and today problem of the day is matching connected group, and which falls under difficulty or category of hard. And the question states that you are given a square binary grid. The grid is considered binary if every value in the grid is either 1 or 0, and you can change at most one cell in the grid from 0 to 1. And you need to find the largest group of connected ones, and two cells are said to be connected if both the adjacent of each group each other, then both having the same value. For example, we having this is a one group and one group of 1 1 1, and if you toggle the third cell to one cell to the second row and the first column. If you toggle that particular cell, you will get a total ones of large group of uh, toggling at most once. You need to toggle at most once, and we will get that answer. And I will be explaining the notebook so that it will be more visualize the answer. See, if you see that the to one cell is 0, if you toggle that particular element, we will get maximum connected as 4, and the sample space 2 will be the here we have 3 by 3 matrix, and if we are tilting any one of the middle elements, we will get maximum component of 7 size. Any one. Here it was showing the last one they are tilting, the third row and second column. They are tilting. It doesn't matter if you build any one of these, it will be at max of 7 only. The expected time complexity n square and auxiliary space is n square. Mm, and the size of the grid is 500. This is pretty much complicated, not that much complicated. It will be very easy, hard. And I will be approaching with two solutions. One will be the brute force approach, and another will be the optimal solution. Whenever the question comes, you have to analyze the key element at most one cell, which means that you have to build at most one cell, and you have to backtrack that operation. So in order to do the backtrack operation, you have to use DFS. And why not BFS? BFS, it will go all over level by level, it will go. But in DFS, it will go one operation at a time, and it will backtrack the operations. It will reverse the undoing the changes. So that is the main intuition. We have to use DFS, and I will be teaching the brute force approach with the DFS approach, and then later on the optimal approach. I will be going with the idea we are using DFS approach to tell the particular operation, and we are undoing that. This is the question, the method given, and in that we have to find the length, and this is the maximum answer to show the result answer, and we are traversing towards the array and check whenever we encounter 0, and we have to build the operation, nothing but changing to one, as I said. And this is the method I was creating the larger area, which internally calls the DFS operation to find the largest connected component. And that value every time we will be checking with the maximum and get the max out of it. And we should undo the changes because at some cases, one operation cannot satisfy the maximum connected component. We have to try out all the operations, and we have to reverse back the operations. At most one, we should building, right? We are talking. So that is the key intuition, and we should adhere to that. And yeah, we will go in with the largest area method. How we are performing, we have to take a visited array in order to reduce the time complexity. This is the better approach. We can get an constant time operation lookup whether it was visited or not. No need to traverse again and again. And initially, we should fill all the values to 0. It doesn't need it because in Java it is always be 0. In C++, we need to fill that instead of garbage value. And this is the final answer, which will be returning the maximum connected component in each individual component. Maximum number of ones are there, and we are traversing throughout the loop and throughout the matrix. And whenever we encounter one, we are calling DFS to count all the connected components, and then we are storing the maximum out of it, and we are returning that answer. In DFS, this is the edge case, the particular row should not exceed the boundary, and the column also, and similar for the negative value should not be or because it gives array index out of bound error if you are doing minus operations, minus index or out of bound ranges, it will get. So first we have to check like this. Any one of this are satisfying, then we can simply return that. That's the reason we are using OR operation, not AND, any one of those. And after that, we are checking for if all are not satisfied, it will come and it will check whether it is already being visited. We are returning that. And this is also for original grid. We are checking whether it was zero. No need to do the operation, simply zero, because we are counting one only. And here we are marking as visited the particular cell. Whenever this condition fails, which means that the grid having one, so we should mark it and we should call all of its neighbor. It's simple. All of its neighbor like left, right, up, and down. And we are adding each one because each component, each element contributing to the one of size one, and so that we will get total count of TFS and total count of number of ones in one individual component, and we are checking the max mode of it, and we are returning that. And every time we are doing, we are talking the particular cell, and we are checking, calculating all the connected components and existing components and taking the max of the fit, and we are undoing the changes. And if you cannot find the minus one, which means that all the matrices are one, no need to compute anything. So this is the last we have to check edge case. So the total answer will be the number of the cells, nothing but n into m, and we can return that max answer. So the time complexity as n square, because we are iterating here n square times, and inside this larger area we are again iterating the array to find the total number of adjacent components and their length. So n square solution, it's not applicable. It will be applicable only less than 10 or 12, n equal to 12. That kind of size it will be suffice. And the interview will ask about to optimize this solution. You can optimize this idea by pre-computing the size, and we'll be storing that. Here the grid of consists of one, and you can see that if you are toggling this cell to one, we will get a maximum area of five. At max, we can find five only, the size of five. And I will be using DFS approach, same thing. As you can see, this is the maximum connections, and we are iterating. This is the area we are storing the size of an individual array in order to avoid another iteration, right? Another traveling throughout the array inside the larger area. We can store this. We can pre-compute and we can store this into one two-dimensional array so that this extra n square solution will be avoided. That is the main inclusion of expected approach. Okay, and while here coming to the this is the area which will store the individual component, each cell individual component and their area itself. That's the reason I was storing area for individual cells, so that I will be taking some buffer as plus two, and I will be implying each cell have to store their areas itself, right? So that's the reason, and then plus two, and we are iterating through, we are traveling towards the matrix and check if it is one, and use the DFS to find the connected components and update their area. We need to update their area and we need to find their connected components. So this DFS calls to here, and it will perform the DFS operation. The index, it will be stored which index we are performing, and that will be stored here. And in the neighbor side, neighbors array is nothing but uh, this is the direction, and so this neighbors, right? Yeah, neighbors is coming from this is the method neighbors, and neighbors of the cell to find the four possible directions. Nothing but the directions as you seen, right? Left, right, up, and down. These directions we will get, and these are the edge cases, the boundary conditions check, and then we have to store into our answer. And once we got the array list, we can iterate towards the array list, and we will be checking by n, which will get the row index. By mod, we will get a column index. With the help of that, we will need to check whether it was connected one or not. If it is one, we have to store that index and call the dfx to the adjacent, whatever the child node, we need to call that on top of it. So the total computation should be done at the end. At the end you will get a maximum area, and this is the another second iteration. Why we are doing? Because we need to set particular cell, right? We are pre-computing and storing into the answer. The first thing is done. This is for toggling the at most one cell and storing the maximum answer to it, so that we will be taking on a hash set and to store the answers. Whenever we encounter zero, we are start iterating towards its neighbor, and we are storing in a hash set, and we should calculate those hash set area. See, usually we are iterating towards the hash set, and their area is cumulate to that and find the answer out of it and return the answer, so that you can get the maximum area of the cells. And the alternate approach will be the uh, disjoint set union. This algorithm is pretty straightforward, similar to the earlier one. Instead of using DFS recursion call, we can avoid the stack overflow error if more number of function calls happens. To avoid that, we can use DSU, disjoint set union. Okay, for a similar approach only. In Fusion, the finding out all the components having the value of one and store their sizes as sizes nothing but area in a DSU, in a disjointed data structure, and find out all the cell with the value of 0 and convert into the cell to 1, and find out the adjacent component and calculate the size formed by the cell we tempered, and we have to check the final answer. We have to compare with the answer. So this is the given matrix. If we toggle this cell, we'll get a maximum size of 7. And we are storing each component and their size. That will be stored under DSU, that structure. And coming to the DSU, we have two property: rank, parent, and size. Size indicates the size of the DSU, and rank indicates the this is we are dealing with the sizes only, right? A rank is not needed as per the basic standard approach. We are using that, and this is the initialization process. We need to copy all the operations, and we have to store that. And size indicates always size contains one, each element contributed to one of length one. And parent indicates that where it is coming from. Initially all will be act as a parent for itself, for themselves, and this is the function to find the ultimate parent with the help of node. And we are checking if the node equal to the parent of get node, which is nothing but siblings, both node and mm, other node, so that we can return the individual node, the parent, the common parent. And if it's not a common parent, then we have to find the ultimate parent, and we have to do the path comparison by setting up, which means, if, for example, if we have some ancestors like this, we can do the path comparison. So it internally does like this. This is the parent of one, this is the parent of two. This is the path comparison operation, and we can return that particular ultimate parent. And we are using the unit by size. This is because of we need to union two components. We have to club two individual component and find their total length. For that reason, we are doing that. You will finding the ultimate parents, and if both are, we can simply return that. No need to do the union operation. If both are different, we have to find the maximum size with help of size of u and size of a, the parent size, and whosoever the parent size is bigger, is smaller, we have to set to the parent size so that it doesn't overflow. If, for example, this tree having smaller length and another tree having the larger length, we have to connect the smaller length to the larger length we are setting up, and we are increasing their size. Size will be increased to this, the larger one. As you see, V is larger. We know the size of V is larger. We are adding the size of V plus the size of smaller one. For example, this is a smaller tree, this is a larger tree. We have to connect this and we have to increase this. But when it comes to parent, right? Parent is U is the parent and V will be the child. So that is the operation we should perform, and else is opposite to it. Hmm. And valid conditions for the boundary checks, simple. And this the function starts from, and disjoint set will be done throughout each individual cell. That's the reason n square. This is more important. And directions. These are the direction. I can give you another trick. Simple -1. Start with -1, not with 1. Start with 0 and -1, 0, 1. That's fine. For example, if you use like this, you can use 0 as a row and this will be the column. Like this, you can alternate by adding 0 to it. It will act as in a single row. You can add the first indicates row, and each time you can toggle back with one step. First will be the row and second one will be the column. So that is another trick to avoid another array, one-dimensional array. And instead of, you can store five elements, and we are traveling towards the array and checking whether the column is zero. No need, as we are doing the first for storing, computing and storing into the DSA. As you can see, whenever we encountered one, we are traveling through their adjacents and checking the valid boundary conditions. If both are one, adjacents also one, then we can union both the adjacent nodes. Nothing but this is the one node, current node. This is the adjacent node. We are unioning their sizes so that we will get each time we will be getting the maximum size out of it. And then after doing all the operations, this is the second traversing method, second time, to find the zero. If it is zero, if it is one, we can continue that. This is the most important. This is like pruning. We can avoid the number of posts, and we are using hash set to store all the parents, and we can sum up their sizes. As the earlier approach, as I discussed, same thing. Like storing hash set will be the unique. All the unique parents will be there. Like columns, column indexes. Hash set will store column indexes, and their sizes will be getting with the help of DSU. DSU dot size get this component. We will get a size and accumulate those total size and check the maximum out of it. And this is where we are traversing throughout the individual cells, individual neighbors, and checking whether it's valid conditions. And if it is one, we can add into to our answer and finding the ultimate parent to it, and storing the answer, and we can add sum up all the unique columns adjacent components, and we can add up those. And yeah, this is the another iterations we are doing. If suppose all are ones, no need to do that. We can simply add the maximum of any one of the cells. Like for example, if you have the matrix, all are one, then we can handle this with the help of this condition. We are traversing throughout the DSU and find the max out of it, max size, and we can return that. And uh, for finding the node and with respect to adjacent node, right? That is where the intuition come here. And the parent indicates the disjoint set parent indicates like this, and each indexes, right, we have to store that, like we have to allocate each cell into this particular index reserve. For that reason we are using this formula, node and the current node and the adjacent node. Current node, how we can find out? Row, the current row into n is the constant, nothing but number of rows, n is number of rows and number of column, both are same, and plus column, which will get the current node index that will be stored here. And adjacent node, how we can get? N row into n plus n column. The new row and new column, if you multiply that, you will get an adjacent node, and we can sum of those. That's how we can contribute. Yeah, that's all from it. Yeah, thank you. Please like, say, like, share, subscribe.